Okay, so this is question number 12, October 2024. So here it says a diagram represents a positive point charge. Draw the field lines to show the electric field around the charge. So first you're going to draw the field lines. The field line must be equidistant. Okay, that means that if I draw this line, okay, here, and if I draw this line here, now draw with ruler. Remember, draw with ruler. Okay, I'll explain what equidistant means. You have to draw this line then, and you draw this line. You see this distance here, give me a second. This distance here, both of these distance must be equal. Right? Both of these distance must be equal. Both of these distance must be equal as well. Make sense? Right? So at a specific point, all of these distances should be equal. Make sense? So draw them, try to draw them perfectly. Okay? With the ruler, remember. The next thing you're going to do is draw an arrow pointing away. The reason we want the arrow to point away is because we base the field lines on a test positive charge. So this is already a point positive charge here. So imagine I put a positive charge, right? They will repel. So you will put a repulsive field away. Make sense? So that's how you draw it. Now, the next thing you have to realize is that here we have a positive charge placed at P and a negative charge placed at Q, shown below. P where we have a positive charge, and here Q we have a negative charge. Okay, and this is the point R. Okay, all right. Then they tell us that R is 4 centimeter from P. Calculate the magnitude of electric field at R. The charge at P is 14 nanocoulombs and Q is negative 14 microcoulombs. Okay, so the charge here is 14 times 10 to the power of negative 9 coulomb times 14 times 10 to the power of negative 9 coulomb, positive and negative. Okay, now what's going to happen, you see at this point R, right? Remember one thing, electric field is a vector quantity. Whenever you hear the word field, that's a vector quantity. Make sense? Now, at P, there are two fields acting. Okay? How do you find the direction of field? Assume that I put a positive charge here because our field direction is decided by that positive charge. Then this positive and this positive field will repel. So P will exert a force, or not a force, an electric field in this direction. Okay. Alright. Then Q will attract the positive charge, so it will exert a field in this direction. This is the electric field of Q. Now, you know how vectors work. If they're in the same direction, they will add up. Opposite directions, they'll cancel out. This is something very basic. If you forgot this, I recommend you go back to unit 1 and see vectors there, okay? How we used to do them with forces when they act in the same direction, 10 Newton, 12 Newton, we add them up, right? Same thing. So electric field at P plus electric field at Q will give you the electric field at R. Make sense? Okay. So how do we find the electric field at, okay, I'm just gonna erase this. Electric field at due to P at R, right? How do we find, let me just write here, R, okay? So the formula for electric field is KQ, which is the source by R square, right? So it's gonna be k q by r square, or let's just write r square for now, plus kq by r square. Okay, I'll just put a capital R square is equals to that. Okay, all right, so this is all just explanation. You don't have to write all of this. Okay, I'm explaining very in a simple way and very basics as well. Okay, so now you see P is 4 centimeter away. So here you can write 4 centimeter. Okay, we'll convert it later. And the distance between R and Q is 8 centimeter, right? So the electric field due to Q at R, the distance is 8 centimeter, right? So this is the electric field at P, the electric field at R due to P. This is the electric field at R due to Q, and that will give you the resultant electric field. Make sense? Okay, then you do 8.99 times 10 to the power of 9, and put the charge there, 14 times 10 to the power of negative 9 over 4 times 10 to the power of negative 2 square, plus 8.99 times 10 to the power of 9 times 14 times 10 to the power of 9 divided by 8 times 10 to the power of minus 2 square. Make sense? Okay. Alright. Now, after we add them up, let's see what we get. We get an answer of 9.9 times 10 to the power of 4 Newton per Coulomb. Now, there's one question that might come in your mind. Why did I not take the negative sign here, right? That sometimes pops up as well. Well, if you rewind back in the video, I told this is the direction of the electric field of P, and this is the direction of the electric field due to Q. Make sense? So let's say in vectors, we decide this is positive, this is negative, right? Which means anything that acts towards the right will be positive. Make sense? And anything that acts towards the left will be negative. So let's say that these two are acting to the right, so they must be positive, right? That's why I ignored the negative sign. But if you want, you can put it there, but then later on you will have to ignore it. Okay? You will just have to add their magnitudes, okay? Because you can't put that negative sign, otherwise you're saying that the EQ is acting in this direction. By putting the negative sign and having a negative electric field, right? So if you get a negative answer for this and you put that negative answer and you add it with this, you are saying that the electric field due to Q is acting in the opposite direction. Okay, that's why I ignored the negative sign. Okay, because I just want to add their values, positive values, because they're in the same direction. Make sense? Okay.